Every single liter of seawater holds 35 grams of dissolved salt. If you extracted all that salt and spread it evenly across all the land on Earth, it would form a 166-meter-thick layer. Every continent and mountain range would be buried under a block of sodium chloride the height of a 40-story building. Grade school intuition points to the standard water cycle as the cause. Water evaporates from the sea, falls as fresh rain, and flows back into the ocean through fresh rivers. But if the rain is fresh and the rivers are fresh, it seems impossible that billions of years of this cycle would result in a planetary ocean packed with salt. Our intuition fails because it struggles to account for geological time. The answer to this paradox begins with an invisible chemical process happening on land. Rainwater is naturally slightly acidic. It absorbs atmospheric carbon dioxide to form a weak solution of carbonic acid. When that acidic rain hits rock, it dissolves minerals, sodium, magnesium, and potassium, and carries them into streams and rivers. River water does contain salt, but the concentration is 0.01%. At that level, the mineral content is effectively invisible to our taste buds. Most freshwater lakes avoid becoming salty because they have an outlet, like a river, that carries minerals away. The ocean has no equivalent drain. It functions as a planetary one-way valve. When water evaporates, it undergoes a purification process. The water molecules return to the atmosphere, but the dissolved minerals are left behind. After 4 billion years of salt flowing into a closed system, the ocean should have become hypersaline, lifeless wastelands. Mathematically, the global ocean should look exactly like the Dead Sea. The fact that its salinity remains stable at 3.5% indicates that a massive mechanism must be removing the salt. In 1977, a deep-sea research expedition near the Galapagos Islands discovered a process that changed our understanding of ocean chemistry. Scientists found massive mid-ocean ridges and active underwater volcanoes that release gases and chloride directly into the deep sea. Along these ridges, seawater seeps into tectonic cracks and hits rock heated to 400 degrees Celsius. This superheated, mineral-loaded water then shoots back up into the ocean through hydrothermal vents. This process dissolves metals like iron, zinc, and copper directly out of the Earth's crust, adding them to the water. These vent systems also function as an active filtration network. The intense heat causes chemical reactions that strip certain elements out of the circulating seawater and trap them in the rock. The ocean floor acts as a massive chemical processing plant, cycling the entire volume of the ocean through these vents every 10 million years. Ocean chemistry is dictated by residence time. The duration an element stays in the water. Iron's residence time is only 200 years, removed almost immediately on a geological scale. But a sodium ion remains trapped for 260 million years, and chloride even longer. Seawater tastes like table salt because sodium and chloride are the two elements the ocean is least efficient at removing. The ledger is finally balanced through physical removal. Sea spray carries salt inland. Minerals crystallize into sediment. Marine life absorbs calcium for shells. Salinity has stayed stable for hundreds of millions of years because the rate of salt entering the water is perfectly offset by its rate of absorption. This suspension of dissolved salt changes the physics of the water. Saltier water is significantly denser than fresh water. This density difference drives thermohaline circulation. In the North Atlantic, salty water becomes dense enough to sink, acting as a pump that pulls warm surface water from the equator toward the poles. Salt also lowers the freezing point of the ocean to -1.8 degrees Celsius, allowing the polar oceans to remain liquid and sustain ecosystems in extreme cold. Western Europe remains temperate because of this salt-driven heat transport. Without the density provided by salt, the pump would stall, and the climate of the Northern Hemisphere would radically destabilize. NASA is looking for this same salty hydrothermal signature on Jupiter's moon Europa. If confirmed, it suggests that rocky geology and liquid water naturally produce salty oceans across the universe. Ocean salt is the operating fluid of a planetary climate engine and a universal prerequisite for life.